random variables. That's when you're doing transformations.
So I wanted to give you guys, in day one, a basic primer on statistics. I know that at this point in your careers, you've probably all had to take statistics, and depending on where and how you took that statistics, you may have gotten something out of it and you may have gotten nothing out of it. I know it took at least 2 rounds of statistics for me to start appreciating why and what and how it all sort of fit together. And again, you have some readings in the general ecology book that talk really mechanistically about how do you do a t-test. And that's not the sort of level of detail that I expect you to know. It's something you should certainly have done in a statistics class. But for the purposes of this, I want you to be able to interpret your statistics and think about what are you actually testing and how do you design a statistical question. So I'm going to have a number of sort of highlighted terms that I think are important, intersperse it with some of my favorite webcomics, and please interrupt me if you have questions, because statistics is complicated. So the basic idea of statistics is that you can make an inference from your data. So you're going to try and draw some conclusion from the data that you've collected. When we talk about a population, populations have a number of different definitions, but in terms of statistics, the statistical population is the entire data set, right, about which you want to make conclusions. You are probably never going to collect all of the individuals in your statistical population. And that's where you're trying to make inferences from the statistical sample that you are going to collect out of your population. And let's compare that to the definition of a biological population, which is just an aggregation of individual organisms of a single species. And note, the single species is an important part of the definition, inhabiting a given area. When we sort of de-abstract the statistical sample, then we have to think about physical samples. So it's really just the portion or subset of something real that you're collecting, or you're collecting information about. And it could be biotic, it could be abiotic. Okay. So inference. So the goal here is to use data from our statistical sample to calculate statistics and to draw conclusions about the statistical population. So we've got our statistical population, and there's some probability that the samples that we're grabbing in our statistical sample represent what's going on in our statistical population. And from that, we're trying to make an inference about the statistical population. So one of the first things that you really need to consider when you're doing an experimental design is how are you going to select your samples? And one thing you're going to see come up over and over and over and over again is random. Randomness is something that is really important to consider when you're collecting data. And part of that is your sample must be representative of the population. Like one of the things I hope you guys experienced while you were running your transects today is depending on where you located your transects, they may or may not have been representative of what was going on in the creek. If you ran one right under the bridge, you probably got a lot of bare ground in your transect. But if you ran it, 10 yards out, you probably got a lot more vegetation. Both are true, both are accurate representations of what was going on at that particular location, but it may not be representative of the population that you're interested in, right? So the most sort of simple approach to a sampling design is random sampling. And so you're collecting individuals that are sampled independently, and that your likelihood of selecting any one individual is equal. Like anybody in the population has an equal chance of being grabbed. And that given the assumptions of statistical distributions, allows you to sort of more accurately represent the population with your samples. However, there's often occasions in which you know there's something else going on and you expect that the population is responding differently. And so this is an occasion where stratified random sampling can help out. So you maybe divide your population into subpopulations of some particular variable that you're interested in. So maybe you're interested in mice in a grassland and a forest. Maybe you would subdivide the populations in the forest from the population that's in the grassland, and you would base your sampling randomly still, but just within each of those subpopulations. Because you wouldn't want to just have forest and grassland and randomly assign your treatments, in which some context you may end up having all of your samples from the grassland and some other subset from the forest. So you'd want to have some equal distribution. And one thing you really want to consider while you are designing a study is bias. And bias is just whether your value is consistently high or low, or your individuals you're selecting are not completely random. Bias can be an issue, and certain methodologies will absolutely give you biased results. That's not to say that you can't correct for biases. So it's not inherently a problem that a sampling method is necessarily has some bias to it, as long as you can recognize what that bias is, and if you need to answer your question, be able to address it and identify that it occurs. In the field, sort of the practical nature of it is you can get randomness from things like random number generators or tables of random numbers, and actually your book has some random number tables, and it describes explicitly on how to use those random numbers in the random number tables. Okay, so one thing that you probably also discovered while you were out running your transects or quadrats or however you were doing things is that sometimes it is just not possible to count everything. And so subsampling is something that often comes in, particularly when you're talking about things that are numerous and you have, say, you grabbed a big chunk of soil and you want to look at invertebrates. You probably don't want to sift through, a ton of soil, but you could subsample and understand what's going on in that, as long as your samples are independent and distributed throughout your sample. So anybody in your sample would have an equal likelihood of being collected. So, and it's really just something where your processing or analyzing of the big sample would be just not possible. And so this is an example of basically a plankton splitter. So you would pour an entire sample inside this round thing. You would sort of flush it back and forth, and then there's a glass piece splitting half of it. And so when it's up here, when the thing's rotated down here, all the sample is mixing up, and then you turn it down here, and half the sample is on one side, half the sample is on the other side. Pour it out into here, and then you've got a subsample. And you can keep on doing that until you got a sample that is going to be representative, and it's going to be random, and it's going to let you not spend a year processing a single sample because you want to get many samples. Okay, and we may use something like this in class when we're doing invertebrate sampling, where you can grid a tray and spread a sample out on your tray, and you can collect just from certain grid squares that you could randomly identify with your random number table. Okay, replication. So a pet peeve of many biologists is that data is actually plural, and datum is the singular. So for any single datum, or a single data point, it's probably not going to be an adequate representation of some characteristic. So let's talk a little bit about what would you expect if you had this graph. So we've got effort on this axis, and we've got a number of species on this axis. What would you expect might happen?
Positive. Yeah.
So you guys are saying something like this is what you'd expect. So you put in some amount of effort and you get some number of species. Does that seem like a reasonable approach? Do you think that this goes on forever?
No.
Do you think at some level of effort you may?
Yeah, it's gonna plateau.
So
once you count them all,
yeah. So assuming that depends again. It depends on the kind of critter you're interested in, or plant, or whatever. It's like if you're interested in mammals, you probably would hit all the mammals at some point. But if you're talking about bacteria, there may be more than you could ever. So you guys are saying something like that might be a better approach. So this is basically the idea of a species sampling curve and a performance curve. And you can do statistical calculations, which I'm sure you guys maybe experienced in your statistics class, on trying to calculate statistical power and trying to assess whether you can actually make the sort of inferences that you want to make given the data that you have. So here's an example of actually some of my work looking at fish movement in a river in New Mexico. And I was really interested. One of the big questions in movement ecology is, are you actually representing with the individuals that you're selecting the actual sort of dynamics of what's going on in a population? And we'll talk too about methods for looking at animal populations and animal movement. And one of the techniques is radiotelemetry. And radiotelemetry, particularly in the past, was something that really restricted you to a small number of individuals at any given point in time. And so I used a different technique called pit telemetry, which we'll also talk about, and said, okay, if I tag some number of individuals and I randomly select them out of my total data set, how is my total average movement, or my maximum average movement for the population, going to change depending on, is it going to change in different years? And so what I saw is in 2008, it didn't take very many individuals for me to sort of achieve that maximum average movement, which described what was going on in the population. But in other years, it kept on going up. And so potentially behaviors were different in different years. And so I'm trying to use this as an example of thinking about how many samples are you going to do, and are you going to sort of get to this plateau or somewhere adjacent to sampling the true representation of what's going on in your population. Okay. The accuracy versus precision component. So I suspect you guys have all seen this figure many times, or something similar to this figure many times. And when we're thinking about statistical designs, and when we're thinking about making inferences from our data, you want to think about what do your data look like, and how is your measurement technique going to tie together to the results that you have. So in an ideal world, you have a measure that is both precise and accurate. And in this, we're using accuracy to be defined as the difference from the true value. In this case, the bullseye is our true value. And precision to be, well, how close together are your samples? If you're going out and, say, measuring a transect, if you measure the transect and then you measure the transect and somebody else measures the transect, are you going to get a tight relationship between those values, or are you going to get something that's really diffuse? And so here is an example of a value that's precise. So everyone's application of the method was very similar, and they ended up getting very similar results. However, it still didn't actually meet the what we thought to be the true values for that. And this is somewhere where confidence intervals and probability really help you understand how confident are you of the value you're saying, and how close is it to our true value. Yep. Okay, so I know that you guys have all seen descriptive statistics before, but these are often things that you're going to report when you're talking about your data. And what we have here is it's really important to think about, depending on the distribution of your data, whether a mean is actually going to represent your data very well. And so in the case where you have a symmetrical distribution, where there is some true mean and everything's just sort of a bit of a deviation, but evenly on the high and the low, the mode, the mean, and the median all pretty much tell you a very similar story. But when you have more skewed distributions, the mean may either over or underrepresent what's actually going on in your data. And so depending on the types of information that you're gathering, you want to think about, like, a great first exploratory step is just looking at the distribution of values and seeing, is the parameter of interest going to represent sort of what's going on in my data set. Okay. So, uncertainty and confidence in the mean value. So, by tradition, people use alpha, the Greek letter alpha, to represent a desired significance level. And when we say a significance level of 5%, we're basically saying that we're confident within that 95% of the time that this thing is true. You're going to see in all the literature, everybody's using 0.05. But you can change it. You're probably going to have a difficult time getting it published if it's somewhere greater than 0.05. But one thing I really want to emphasize here is that statistical significance is not always biological significance, and vice versa. Say you had, I think they give an example in the text of, two groups of mice, and they weigh the different groups of mice, and there is, because they had a large enough sample size, a statistically significant difference in weight between the two populations of mice. But that difference in weight is like 0.2 grams. Depending on how big the mice are, it probably doesn't matter. Like 0.2 grams, probably not a big deal. But so that's a case where it may be statistically significant because maybe you had a large enough sample size, but it's not really biologically significant. There isn't really a big difference between the different populations. You've probably all calculated a standard deviation at some point, and it's really representing how far your data points are from the average within your population. Standard deviations are kind of tricky to compare between different samples. And so this is where something like a standard error and a confidence interval come into play. So the standard error is how far our sample estimator, which is, when I say sample estimator, I'm meaning a mean or some other summary statistic, may be from the population parameter of interest. Remember, our statistical population. So how far is the sample mean that we collected, from our statistical sample, how how far is it from the true population mean? And so that's something that's much more easily comparable between different samples. And a confidence interval is this interval where within a stated level of confidence, we can say that it includes the mean. If you have really, really variable data, your confidence intervals are going to be really, really wide. If you have really precise and accurate data, your confidence intervals are going to be really tight. Does that all make sense?
Could you say confidence interval again?
Sure. So a confidence interval, and you can see how to calculate statistical confidence intervals. It's going to be dependent on the distribution that you think is relevant to your population. But it's this interval around your points. You've got your mean or whatever.
Mm-hmm.
It's the interval that you say, okay, I'm 95% confident that 95% of the time, if I took samples out of my total statistical population, I would get a mean within these bounds. Does that make sense?
Yeah.
So it's like you're saying, okay, I've got a jar of marbles.
Yeah, your mean's 12, but your confidence interval is between 11 and 13 or something like that.
And
That's
so
95% of the time.
95% of the time, I'm going to take a sample out of here. My mean value is going to be between these two values. So confidence intervals are really powerful in telling you how well do you actually understand what's going on. Okay, you've definitely seen these before. But it's really helpful to think about when you're trying to present your information to somebody, present your data to people. And that's the dependent and the independent variable. And excuse me. On your x-axis, you're going to have your independent predictor variable. It's the factor that you've controlled. You can also have covariance, something that's not controlled by the researcher on this. So maybe you have two things that are going to change in the same way. So maybe water level and water discharge are going to change in the same way. Those could be on that axis. And our response is going to be on the y-axis. And so that's generally the answer that we're looking for.
Which one did you say was on the x-axis?
So independent,
Independent.
independence on the x, independence on the y. Okay. All right. So these are the types of data variables that you might collect, and depending on what types of data you collect will then translate into what statistical tests are appropriate. And also sort of think about it as what are the questions you're trying to answer, and when you're collecting data on a data sheet, it's like, do you want to have grouping variables or do you want to have some sort of continuous variable? And so the first...
And the tests depend on that.
The first two, yeah, the tests completely depend on what you select. So the nominal values, so that could be like you go out and you name your transects Joe, Bob, Mike. Doesn't really matter. There's no intrinsic order to them. In ordinal variables, there is some particular order to them, and so you may want to have an analysis that considers the order of your variables. Discrete samples are something that is only going to come in an integer. Usually that's like offspring. You're probably only going to have even or an integral number of integer number of offspring. And then there's continuous variables, and those are often some of the environmental variables we might collect. Okay, so experimental design. The most important thing about experimental design, I would say, is a control, and choosing an adequate control. And there's a good description of that in the Carbon book. The control is really what you're comparing something to. You don't necessarily expect your control to change over time, or at least not to change in any way related to the experiment that you're doing. And it really comes back to the question that I posed to you originally of what are we restoring to? Like, what is the baseline at which we're trying to compare our information? So we also talked a little bit about randomization, and the idea of randomization is really just to prevent this unintended bias in your sample, that you're collecting and everyone has an equal chance of being selected, and so you're getting something that's representative of the total population, provided you have enough replication. Replication is what helps you pin down those numbers, so it gives you the precision of your in your experiment. Blocking is a term that you should be familiar with. We're probably not going to use it in this class, but blocking is a statistical method that lets you reduce some of the unexplained variation in your data set. And so that's something where, say I think the example they give in one of the books is like you have different farm fields and they have a different angle to them. Some are flat, and so they drain in particular ways. And some are don't drain very well, and some are angled, and so one part of the field stays much wetter than the other. You might want to block your samples or your experiment based on these conditions you know could be affecting what's going on there, but that's not your experiment. You don't really care if the angle of the slope does something to the vegetation. You just care if there's a difference between those. And so you can take that variation out by identifying a blocking factor. Okay, so hypothesis testing. You're usually trying to do hypothesis testing on the parameter of interest, and in our cases, it's almost, I'd say it's generally the mean. And when you're trying to build a hypothesis, you need to have a null hypothesis. And basically, your null hypothesis is something where you're expecting no effect and no relationship amongst your variables. You can have multiple alternative hypotheses, and it's basically what's not consistent with our null hypothesis, and trying to ask, is there a difference between our groups? And some of the tests that you guys might have encountered, like t-tests, you can have one-sided t-tests and two-sided t-tests. And those are really sort of posing different hypotheses. So a one-sided t-test could just be looking at one side of your distribution. So in this case, we have our alpha, which is 0.05. So 95% of the values should be coming from in here, and we would want to say that these populations are different if they fell in these tails. And because we say we wanted to have 5% of the chance, we have 2.5% on the top and the bottom of our distribution. But say you were only interested in understanding whether it was greater than. You could have a one-sided t-test that's only looking if it's greater than. And usually your statistical programs will give you a one-sided value and a two-sided value. So thinking about null hypotheses, one of the things you'll see described, and something that we'll talk about a little bit next lecture or the lecture after, is false negatives and false positives. And so in this case, we have a case where the null hypothesis is true. If we did a statistical test and we rejected the null hypothesis, that's called type 1 error. And that's a false positive. So we said there's a difference, and there's not really a difference.
Because your sample size isn't big enough or something.
Or something is going on with it. In this case, we did our statistical test. The null hypothesis is true, and we failed to reject the null hypothesis. So that's the correct inference that true and it's negative. The other one to be really concerned about is type 2 errors, which are false negatives. So the null hypothesis is actually false, but we failed to reject the null hypothesis, as in there was actually a difference, and we weren't able to detect that difference.
Aren't the type 2s worse than the type 1s?
That depends on your question, right?
Yeah, I guess.
Like, if you are, say, trying to do, so false positives, I'm going to talk about it in the context of environmental DNA. So people are trying to say, I'm going to go grab a water sample or a soil sample or something, and I'm going to take DNA out of that. I'm going to compare it to against a bunch of different primers, and I'm going to say, these species are present in this location because of the presence of their DNA. Well, there could be other reasons why the DNA is there. Maybe an animal ate that animal and then pooped there, and then their DNA is there, but the animal was never there.
Right.
So if you were, say, somebody managing non-native species, and you were looking for the expansion of, say, Asian carp in the Midwest, and you were doing eDNA, and you get a high rate of false positives, that's a big problem because you're going to try and make management decisions based on that, but that's problematic. There aren't actually any Asian carp in the area, and you said there were because your test gives you a lot of false positives. So they both can have drawbacks. You generally want to be able to reject the null hypothesis when the null hypothesis is false. Okay, so hypothesis testing. The test statistic, and I always have a little bit of a hard time wrapping my head around the test statistic, and this is basically something out of a distribution. And distributions are generally related to the sample size that you have. So you can see from this figure, this is a t-distribution with a number of samples less than 30, and this is a t-distribution with a number greater or close to 30. And you can see that our understanding of the mean is much wider, and it would be much harder to reject something in here because the tails, a lot more data is out in the tails than it is when you have more samples. And so this is the z distribution is the standard normal distribution. Different statistical tests have different test statistics, and in the old days, like as represented in your textbook, you would go to a table and you would look up your test statistic. You can generally have a statistical program which will actually calculate the test statistic. And so your test statistic is looking at the difference between what's observed and what you expect under your null hypothesis. So really just like what's in this center given your alpha cutoffs. Okay. So we already talked about the null distribution, and the p-value is the probability of wrongly rejecting your null hypothesis. Okay. So we're going to step back a little bit, having talked about sort of the general distributions, and think about power analyses. Power analyses can be really challenging because it requires you to know some things about a data set that you haven't collected yet often. And so the literature is often a good place to start when you're looking for some of these components. But so with any three of these values, you can calculate a fourth. So if you're trying to figure out, well, what sample size do I need to be able to reject my null hypothesis if there really is a difference, you would say, okay, well, what significance level do I want to be able to reject that? So it's the probability of finding an effect that's not there. You would say, what's the effect size I want to see? And that's really the one that's the hard part to pin down. How big of a difference do you want to detect? So, like, depending on what sort of metric you're thinking about, it may be difficult to identify exactly how big of a difference you think is important. So say you were going to go,
Should be different.
yeah. So say you were going to go collect aquatic invertebrates, and you want to be able to detect differences in the density of aquatic invertebrates in your creek, and say you have 5 per meter squared versus 15 per meter squared. Is that a difference that is relevant? You have to think about, well, what do I want? How big of a difference do I actually want to detect? And there's a difference between, say, 5 invertebrates per meter squared and 7 per meter squared. Is that something I want to detect? I'm going to say that the smaller effect size you want, the bigger the sample size you're going to need. And then you're going to be able to calculate your power. And again, these are looking at your probability of type 1 and type 2 errors. Okay. Theoretical assumptions for statistical comparisons. Generally, for many statistical comparisons, and there's often sort of asterisks to these, is we expect that the populations we're trying to compare have equal variances. And generally, most of the commonly used statistical tests assume that your population is composed of data that conform to a normal distribution. And those are things you often want to look for prior to doing your data analysis and seeing how badly are you violating these assumptions. In the case of ecological data, you often are somewhere close to violating these assumptions, and particularly when you have smaller sample sizes, it may even be difficult to detect or to determine what the distribution of your data is. When these two things aren't true, for a lot of the traditional statistical tests, you may have to use some sort of data transformation. And some of the more common reasons you might need to use a data transformation is something like a proportion or percentage, because those are bounded values. You know, you can only, you can't have a percentage really greater than 100%, or a proportion, it's all sort of bounded in a restricted area. There's been some thought on whether you need to do transformations on data involving counts, but people have sort of changed their perspective on that. And data where your relationships are nonlinear, you may need to do transformations. Okay. So when you're trying to interpret your p-values, generally you don't really want a data set that has lots and lots of extreme outliers. So data that are well outside of the range of the majority of the data. The individuals that you're sampling shouldn't be dependent on each other. So say you wouldn't want to count 2 clones of the same willow and expect those to be independent if they're connected underground with the root, if you were interested in some particular parameters. You generally assume, for sort of the traditional statistical tests, that your data are symmetric and that you have a single mode. And remember, a mode is basically that top point of your peak. And a bimodal distribution would be something where you have 2 humps. And as you get more and more data, it sort of matters, or more and more samples, it sort of matters a little bit less. One thing to consider is your statistical tests aren't proving your hypothesis. They're saying within a particular probability that you don't have, you have insufficient evidence to reject your null hypothesis, not that your alternative hypothesis is false. So even though you didn't reject the null hypothesis, you can't say
false.
You can't say that your test was absolutely false. You can say there's no support to it. Oh. Maybe you can read the cartoon. I thought it was fine. Okay. So, did I know? Well, I thought I had an explicit discussion of t-tests in there, but or at least written on the graph. Most of the stuff I was previously describing is related to t-tests. And again, they describe in glorious detail t-tests in your general ecology methods book. What we've talked to up to now has really been the comparison between two populations rather than between many populations. And an ANOVA is a means that allows you to compare, or a method, sorry, that allows you to compare multiple means. And your response should usually be some sort of continuous variable, and your factors should be a categorical variable. So that could be one of your ordinal or your nominal values. In a one-way ANOVA, so you'll often, when you're doing, say you're writing a paper for publication, you would generally describe the statistical test that you did to approach, to get at your data. A one-way ANOVA is an ANOVA that has a single factor, even if you have multiple different populations that you're testing. You're just testing the effect of soil moisture, for example. And in the case of this, your null hypothesis is that all of your means are equal. Your alternative hypothesis is that at least one of these is different. And think about what that means. Your statistical test here is just saying that one of your populations is different from the other, or maybe multiple populations are different from each other. And in order to get at which populations are different from each other, you have to do a subsequent test. And is it my next? I thought I had another slide in there, but basically, if you think about a t-test, you could test each of these populations to each other using a t-test. You have two populations you're testing them. But remember that all of these statistical tests are saying there's some probability that you can't reject the null hypothesis. So that's where this joke is coming in. So they're testing a link between the purple jelly beans and acne. And they keep on testing all the different colors of jelly beans and acne. And in one of them, they find that green jelly beans have a connection to acne.
Smaller.
So
There's a difference.
So then the news article says, okay, green jelly beans are linked to acne. But the joke of this is that just by chance, if you do more and more statistical tests, somebody's going to end up as a false positive. And so it may not actually be that there's a link between green jelly beans and acne, but that just because of the statistical process, you end up getting that relationship. And so that's where the ANOVA is coming in, because you're not having to do multiple tests, and they've established ways of doing post hoc corrections for the sort of multiple comparisons that you're doing. And so in this case, here's some other work that I had done where we were looking at algal growth on nutrient additions. So we had put out little clay pots that had nutrient additions coming out of them. And we wanted to know, is there more algal growth on ones that get nitrogen, phosphorus, or nitrogen and phosphorus together? And so we were able to do a post hoc test, which would test the differences between all of these and identify which ones are grouped together. And so that's what these letters indicate. So you often see that when you're reading some of these journal articles. You'll see people either putting an asterisk between, or letters, or numbers, or something indicating which groups are different by their statistical test and which groups aren't. And so even though this one has a fairly large error because of replication, we were able to say that these ones were similar and this one was different. So, okay. So sometimes you violate a lot of assumptions, or your data violate a lot of assumptions, and so some of those statistical methods may not be appropriate for analyzing your data. And some of these cases could be like when a median maybe describes your data better than the mean, or is more representative of what's going on in your data than the mean is. And you often get that when you have a skewed distribution one way or another. And it's sometimes good for testing procedures that don't depend on certain assumptions of mortality or equality of variance. That you don't have equal variances between your two populations, like one's really variable and the other one's not so variable. A non-parametric test may be able to help you there. However, the challenge with non-parametric tests is that they, again, just sort of tell you that that there is a difference between your two treatments. You can't calculate a confidence interval off of that without some very complicated math, and it doesn't necessarily tell you by what degree those things differ. So with your t-test, you can say the means are different and how much are the means different. With a non-parametric test, you can say the means are different, but you can't really say how much. And let's see here. You're throwing away information. So they describe pretty nicely what you're doing when you're doing one of these statistical tests, and you basically, in a lot of them, you're sort of like taking your data and sorting them in a particular order, and then it's the order of the data, not the actual values, that's being used to determine whether there's a difference or not. And so the take-home message is, in general, non-parametric tests can't really be as powerful in the statistical sense to detect differences as our parametric tests. But sometimes it's the only option that you have. Okay. So I think I have you calculate maybe a goodness of fit somewhere, maybe I don't. And so this is basically looking at frequency of occurrence data and basically asking, is the observed frequency of what we see, does it match the expected of what we would expect? So in this case, we have substrate of 50%, 30%, 20%. Our initial assumption would be if animals didn't really care, particularly about one substrate or another, that they're going to match up. The numbers of individuals are going to match up with the abundance of that habitat. No, that's all I have? Huh. All right. Okay. Yeah, which is good because we're almost out of time. So, linear regressions. Linear regressions are something you're going to use when you have continuous variables on both axes. You're generally fitting a line that you can do nonlinear fits. In the case of linear regressions, your R2, or your R squared, is the coefficient of determination. And so it's really just saying, okay, how close are the individual points in my data set to the line? You can calculate p-values and confidence intervals from a linear regression. And the really great thing about a linear regression is you can use it to predict things that you didn't measure. You generally want to do that within the realm of reason. So you wouldn't want to say, measure the weights of a little tiny trout and a medium-sized trout, and then extrapolate to the biggest that a trout could ever be, because the relationships may be different depending on which life cycle you're talking about. And linear regressions don't necessarily, even though it sounds like it's a linear regression, it's got to be a straight line, depending on if you transform your data. So if you use log axes, you can basically make curved data be linear, and you can fit them with a linear, but then you have to do some back transformations of log values. But it is possible to do linear regression on non-linear data. Okay. So I'm going to give you an example of a place where linear regression may break down. So when we're doing a linear regression, actually ANOVAs are similar. You have residuals. Basically, it's the leftover data. It's what isn't being explained. And in this case, it's really the vertical differences between the observations and our fitted values. And so if your residuals have some trends to them, that means your data isn't fitting very well. You generally want your residual data to basically be noise, just random. And here you can see, so this is a linear fit, which is with natural logs, of mobility versus the density of an animal. And you can see at the lower values, there's trends in the directionality of our fit. So it's under-predicting here and over-predicting here. So the general message I want you to get out of here is your residuals are something you should look at, and that there shouldn't really be trends in your residuals.
It should be random.
Yeah. And okay. So one approach that you can take is a nonlinear regression. The problem with nonlinear regressions is, well, they used to be really mathematically challenging to calculate. Computers have gotten substantially better, and it's more easy to fit some of these models. But it remains that there's still a challenge of trying to determine what the effect of your predictor is on the response. It's not necessarily as intuitive as a linear response is. I think I write p-values are impossible to calculate. I think there are some methods that will calculate p-values, but generally it's not a trivial thing to calculate p-values, and you may or may not be able to calculate a confidence interval for these.
Because the data is not distributed normally.
I don't like that's beyond sort of my mechanistic understanding of what's exactly going into a nonlinear regression. Okay. One thing that you will probably encounter at some point in your career, particularly as Bayesian statistics become more and more popular, is, has anybody heard of a Bayesian approach to statistics?
Reading critical.
Yeah, it's not generally commonly taught yet. It's something that ends up showing up in more advanced classes. But most of the statistics classes that you take still are frequentist statistics. And all the stuff that we talked about up till now were frequentist statistics. But the Bayesian approach basically lets you say you know something about, or say you have a guess about something that's going on in your data before you actually do your statistical test. And they call it assigning a prior probability. And so it's your belief about the value before you've actually seen the data. So you have some expected distribution or relationship that you're expecting, and then you can calculate a posterior probability. And so that's how did your belief about that data change after you see the data? And so it's basically a method that lets the statistician learn from experience with a particular piece of information. It's generally these sort of, I think they call them Monte Carlo methods, where it's just basically replicated over and over computer models and that allow you to do Bayesian statistics. I have not yet used Bayesian statistics for anything, but it's certainly something that people who do population modeling, market capture modeling, Bayesian statistics play a big role in those, because being able to assign some sort of prior knowledge to your statistical test can get you better information.
So that would be like last year they did some study that said there was 20 deer in this region, so I would use that value as my prior probability kind of thing. If
You would calculate a distribution that you expect.
Kind of like 3 of
So it wouldn't be like a
these,
point value, but it would be like some expected value.
like a ratio of
Getting beyond, we're getting beyond my my knowledge. I mostly wanted to throw it out there as you're probably going to hear about this at some point in your career, and if you decide to go down like a wildlife route, you may end up being somebody who's a practitioner of it. It's not something you generally have to use for just day-to-day analyses. There are other approaches, general linear models and multiple regression, and that's basically taking multiple effects and fitting them into a general an ANOVA is a form of a general linear model. They have slightly different assumptions. And multiple regression can say you've got multiple parameters that you're interested in. How do those relate to each other? One of the complicated things is something that if you'd followed any of the sort of climate change components, is what components are you including in your model as predictors? The general idea is that the fewer predictors you have, the better off you are. Because the more and more predictors you throw into a model, the better and better your data is going to fit. Even if those don't really have anything to do with the data, just the more parameters you push in there, the better the fit. And so the ideal of parsimony is trying to select the model that best explains your data, but has the least number of parameters. And there are things like Akaiki's information criteria. You'll often see it as AIC in some of the literature that you'll read. It said, okay, we tried 10 different models that some of them had like water temperature and air temperature and algal abundance, and we then used AIC criteria to then say, okay, well, this model that had all the variables doesn't do as well as this other one that has fewer variables but explains the majority of the data. So it's really just trying to winnow down your model to being the things that are actually important. Multivariate statistics sort of come into it in the same direction. So there's something called principal components analysis. I can't remember if they talk about it in general ecology, but I think Carbon talks about it in one of the chapters. And this is basically saying, okay, so maybe you went out and you collected a ton of different variables about something. And in combination, they may overall explain what's going on in your data. So you can use these principal components factors where they basically mush factors together into different groups. And you say, okay, we're going to take, I don't know, water temperature and algal abundance and air temperature, and we're going to put them into one component, and then it throws it into this weird multivariate space that then tries to group the data based on it. So it's a very computationally intensive thing, but it's basically just trying to group data based on some shared factor. And we're not going to use principal components analysis, but you'll see it described in the literature. Alrighty, so that's a very quick and kind of messy description of statistics. The statistics quiz will be focused on